In this video, we will discuss the definition and the different formulas in determining the Laplace transform of a given function. By definition, the Laplace transform of a function f of t is a transformation to a function in terms of s, denoted by this symbol here. So this denotes the Laplace transform of f of t, or we can denote it by capital F of s, is an improper integral which is equivalent to the integral from 0 to infinity of e to the negative st times f of t dt. So, given a function f of t, if you want to get the Laplace transform, what we have to do is just to plug in the f of t on your definition, okay, of the Laplace transform as an improper integral. So, for instance, if you want to determine the Laplace transform of k, where k is a constant, then, using the definition, Laplace transform of k is equal to the integral from 0 to infinity of e to the negative st times your f of t is k dt. Now, since k is a constant, okay, so what we do is we solve this integral, no? So we can first solve this indefinitely. Since k is a constant, we can bring it out of the integral. So you have k integral from 0 to infinity of e to the negative st dt. And now, in general, again, we already took note that in general, from your integral calculus, the integral of e to the mt dt, where m is any constant, is equal to 1 over m e to the mt plus c. So it follows that here, okay, since s is considered as a constant and we are integrating with respect to t, we can write the integral as k times negative 1 over s e to the negative st. Right? Following this particular generalization. And then since this one is a definite integral, we evaluate your integral from 0 to infinity. So here, we substitute infinity and 0 to t because again, we are integrating with respect to t, not in s. Okay? So this one is equal to negative k over s times, okay, so e to the negative s times infinity minus e to the negative s times 0. But take note that e to the negative s times infinity is equivalent to having 1 over e raised to infinity, very large value. Now, this one is equivalent to e raised to 0, so that's equal to 1. 1 over e raised to very large value is actually 0. Okay? And so, this becomes equal to negative k over s times 0 minus 1. And you have here negative k over s times negative 1. Therefore, the Laplace transform of k, where k is a constant, is simply k over s. So it follows now that if I want to get, for example, the Laplace transform of 5, from this generalization, we can now say that it's just simply 5 over s. Or I want to get the Laplace transform of square root of 2, then it's simply square root of 2 over s, and so on. Now, another example, okay, if your function f of t is given as a piecewise function, so meaning it is defined differently at different domains, we have to use the definition, okay, which is the definite integral, because we have to cut the integral, no, from 0 to infinity. Instead of 0 to infinity, we will follow whatever is written, okay, or whatever is the restriction in the domain of your f of t. So here, f of t is negative 1 when t is from 0 to 3, but it is 1 when t is greater than 3, or from 3 to positive infinity. So from our definition, okay, we know that, again, the Laplace transform of a function f of t is equal to the integral from 0 to infinity of e to the negative st times f of t dt. However, okay, this one here, okay, our given function is not continuous, okay, meaning it is not just a single function representation for values of t from 0 to infinity. Therefore, we have to have two separate integrals to evaluate the Laplace transform of this given function. So we write it as Laplace transform of f of t equal to the integral from 0 to 3 of e to the negative st. So from 0 to 3, our given function representation is -1, so that's times -1 dt. And then plus, t greater than 3 represents limits from 3 to positive infinity of e to the negative st times our f of t now is 1, so times 1 dt. And we can evaluate now here, so just like what we did on the first example, in general, this one is negative integral from 0 to 3 of e to the negative st dt plus integral from 3 to infinity of e to the negative st dt. So this is just negative of -1 over s e to the negative st evaluated from 0 to 3 plus -1 over s times e to the negative st evaluated from 3 to positive infinity. So evaluating your integrals, you get here positive 1 over s times e to the negative s times 3 minus e to the negative s times 0 minus 1 over s times e to the negative s times infinity minus e to the negative s times 3. Simplifying further, you have here 1 over s times e to the negative 3s minus 1 minus, again, as t approaches infinity, e to the negative st goes to 0. So you have here 1 over s times 0 minus e to the negative 3s. Combining like terms, we have here 1 over s, e to the negative 3s, minus 1 over s, and then you have plus 1 over s, 1 over s, e to the negative 3s. So we can combine the first and the last term. So you get 2 over s, e to the negative 3s, minus 1 over s. So from the definition of the Laplace transform, we can actually derive from the improper integral Laplace transforms of common functions. So we won't be doing it one by one anymore. Instead, we'll just be giving now the Laplace transform, the formula in determining the Laplace transform of common functions. So here are the formulas. So Laplace transform of k, just what we saw a while ago. Laplace transform of k where k is a constant, just k over s. Laplace transform of e to the kt where k is a constant is 1 over s minus k. Laplace transform of cosine of kt is s over s squared plus k squared. Laplace transform of sine kt is k over s squared plus k squared. Laplace transform of hyperbolic cosine of kt is s over s squared minus k squared. Laplace transform of hyperbolic sine of kt is k over s squared minus k squared. Laplace transform of t to the n is n factorial over s to the n plus 1, where n is an integer, positive integer. Laplace transform of t cosine kt is s squared minus k squared all over s squared plus k squared quantity squared. And Laplace transform of t sine kt is 2ks all over s squared plus k squared quantity squared. So you have to memorize these formulas, okay, and then we will just apply them, okay, to our function wherever is applicable. No, instead of doing the integral, we will just apply these common formulas. specifically for functions that involves more than one term, no? So basically, it's an expression separated by the plus or minus sign. We use what you call the linearity property of Laplace transforms. So the linearity property of Laplace transforms tells us that if a and b are constants and f of t and g of t are functions that are Laplace transformable, then the Laplace transform of the combination of a f of t plus or minus b g of t can be written as a Laplace transform of f of t plus b Laplace transform g of t. So that should be plus or minus b Laplace of g of t. So sinasabi lang dito sa theorem na to, no, sa property na to is that the Laplace transform can be operated, or it can be performed term by term. Okay, just like differentiation or just like integration, it can be performed term by term. Again, as long as the function is composed of terms, no? And you cannot use this in multiplication or in division. So, like say for example, you have Laplace transform of f of t all over g of t. This is not equal to Laplace of f of t over Laplace of g of t, or Laplace of f of t times g of t. This is not equal to Laplace of f of t times Laplace of g of t. So this does not satisfy the linearity property. So only addition and subtraction. Okay, so let's have the following. Use the formulas, no, in evaluating the following Laplace transforms. Laplace transform of 1 over 60t to the fourth plus 2 sinh square root of 2t. So from our formula, okay, you know that the Laplace transform of t to the n is n factorial over s raised to n plus 1. Okay, and then the Laplace transform of sinh kt is also given. So using the linearity property, we can rewrite this first as 1 over 60 Laplace transform of t to the fourth plus 2 Laplace transform of sinh square root of 2t. So we can now write this as 1 over 60 times Laplace transform of t to the fourth, or t to the n will be n factorial. So in this case, n is 4 over s raised to n, so 4 plus 1, plus 2 times Laplace transform of sinh kt is k over s squared minus k squared. So your k here is square root of 2. So that will be square root of 2 all over s squared minus square root of 2 quantity squared. So with this, yeah, 4 factorial is 4 times 3 times 2 times 1. That's 24. 24 over s raised to 5 plus 2 square root of 2 over s squared minus 2. But 24 over 60 is just 2 over 5, 2/5. So you can simplify this 2/5. So this one becomes 2 over 5 s to the 5 plus 2 square root of 2 over s squared minus 2. Second example, Laplace of 5 sine 2t minus 6 cosine 2t. So what we do here is we write using linearity property as 5 Laplace of sine of 2t minus 6 Laplace of cosine of 2t. The Laplace transform of sine kt is k over s squared plus k squared. The Laplace of cosine kt is s over s squared plus k squared. So you write this as 5 times k here is 2. So that's 2 over s squared plus k squared. So that's 2 squared. Minus 6 times s over s squared plus k squared. So you have here 10 over s squared plus 4 minus 6s over s squared plus 4. Now, since the two fractions are similar, then you can combine them into a single fraction. So you have 10 minus 6s all over s squared plus 4. Third example, okay, so in this case, you have a product of t and this factor here, cos pi t plus sin pi t. So you cannot just get the Laplace transform by factor. Okay? Instead, you have to distribute first the t to to both terms inside the parentheses. So you have here Laplace transform of t cos pi t plus t sinh pi t, and then minus 1. Okay, the 1 is not affected by t because it's not included inside the grouping symbol or the parentheses. So getting the Laplace transform, yung Laplace transform of t cos pi t plus Laplace transform of t sinh pi t minus Laplace transform of 1. So the Laplace transform of t, alright, I just fixed the given. It should be, instead of cos pi t and sin pi t, it should only be cosine pi t plus sine pi t. So, continuing this, so after separating using Laplace linearity, you will now have Laplace transform of t cosine pi t plus Laplace of t sine pi t minus Laplace transform of 1. So from the values or for the formulas, okay, of common Laplace transforms, your Laplace transform of t cosine kt is s squared minus k squared over s squared plus k squared squared. So following that formula, so you get Laplace. So Laplace transform will just be, in this case, our k is pi. Okay, here also k is pi. So you have s squared minus pi squared over s squared plus pi squared squared. And then for t sine kt, that will be 2ks over s squared plus b squared squared. So that will be 2 pi s all over s squared plus pi squared squared minus 1 over s. So you can combine the first two terms to a single fraction. So you can write this as s squared minus pi squared plus 2 pi s over s squared plus pi squared squared minus 1 over s. Now for the fourth example, it's basically a product of e to the negative 5t and cos kt. So again, we cannot write this as Laplace of e to the negative 5t times Laplace of cos 3t. Instead, we find a way on how to separate this as several terms. So recall that cos of x is equal to e to the x plus e to the negative x over 2. Therefore, if I have cos of 3t, I can write it as e to the 3t plus e to the negative 3t over 2. So we can replace the given by its equivalent definition using exponential or as exponential function. So you have Laplace transform of e to the negative 5t times e to the 3t plus e to the negative 3t over 2. And then we can just distribute this. So by laws of exponents, you have here Laplace of e to the negative 5t times e to the 3t. You add the exponents, that's e to the negative 2t. And then you have plus e to the negative 5t times e to the negative 3t is e to the negative 8t all over 2, which we can write as 1/2 Laplace transform of e to the negative 2t plus 1 half Laplace of e to the negative 8t. So using the plus transform of e to the kt, which is 1 over s minus k, we have here 1 half times 1 over s minus minus 2. Our k is negative 2 here. And then for the second term, that's 1 half times 1 over s minus minus 8. So simplifying further, you get 1 over 2 s plus 2, and then plus 1 over 2 times s plus 8.